So this video is about an introduction, basically, to complex numbers. First thing that we want to discuss is uh, what we keep seeing in solving quadratic equations was that some quadratic equations did not have solution in real numbers. And the reason the solution would not show up was that we would end up with a negative value under the square root. So, for example, you used to see, let's say, x squared plus 1 equal to 0, and this gives you x squared is equal to negative 1. So you have to take the square root of negative 1. So this actually gave the rise to the fact that people started thinking about square root of negative 1 added two real numbers and would create an entire different type of numbers. And so that's where it started. They started with solving quadratic equations. There was no solution, real numbers. Can we add another number to make our set of numbers bigger, and then creates all solutions to all quadratic equations? And it turns out, yes, if I just add this one and create this complex numbers, and all the solutions can be done using the complex numbers that I create with that. And so now, important property of I is this. I to power 2, as you suspect, is going to be equal to negative 1. So what are imaginary numbers? So again, if you go back to the quadratic equations and the ones that don't have real solutions, some of them are not just square root of negative 1. They're like, let's say, square root of negative 4. So what do I do with that? And so square root of negative 4 becomes square root of 4 times I, which is 2I. So that's an imaginary numbers. And be careful when you're doing this type of operations with I. It has to be, if you have a negative number underneath the square root, you can separate it into the square root of the absolute value times I. But you cannot break down a positive number into, so for example, you could not have done this. This is completely wrong. And so now, what are complex numbers? So again, then the solution of a quadratic equation, which is not real, sometimes b is not 0. In this case, b was 0. Sometimes b is not 0. So you should be able to add a real number to a complex number. So the format, the overall format, so this was an example of an imaginary number. All imaginary numbers look like this, b times I. A complex number looks like this. A, which is a real number, times b, which is a real number, plus b, which is a real number, times I. And for example, 3 plus 2I is a complex number. Now, if I'm looking at this complex number, this part is called real part, this part is called imaginary part. Real part, imaginary part. The fun part of this is that we actually can plot complex numbers in the complex plane. And so complex plane, the the independent variable is going to be the real part, and this part would be the imaginary part. And then, so real part of a complex number a plus bi is a, imaginary part of a plus bi is b, and you plot point AB, and that would be your point a plus bi in a complex plane. Let's do a few examples. For example, if I want to plot 2 plus 3i, 2 is the real part, 1, 2, and 3 is the imaginary part. So this is the point 2 plus 3i. And then if I want to plot negative 2 plus 3i, negative 2 over here, and negative 2 plus 3i. If I want to plot 4i, 4i is strictly imaginary, so 4i. If I want to plot 5, 5 is strictly real, 1, 2, 3, 4, 5, and 5 is over here. Now, as any number, we were expecting some operations with the complex numbers. How do we add two complex numbers? Let's say I'm adding 2 plus 5i, a complex number, plus 7 plus 3i, another complex number. When you're adding complex numbers, you're adding the real parts together and the imaginary parts together. So this would end up to be 2 plus 7, which is 9, plus 5i plus 3i, so add 5 and 3, and you get 8i. Subtraction works the same way. You just have to be a little bit more careful. So if I have 2 plus 5i minus 7 plus 3i, what you want to do is you want to subtract the real parts, which is 2 minus 7, which is negative 5, and then subtract the imaginary parts, 5 minus 3, which is 2i. How about multiplication of complex numbers? Let's write this down again. 2 plus 5i times 7 plus 3i. With multiplication, you FOIL. After you FOIL, remember the important property. So what you not want to see is I to power 2, I to power 3, and so on and so forth. You just want to see one part. You want to see this format of complex numbers. You want to see the real part plus the imaginary part. So that's the purpose of using this property and the addition of complex numbers to clean it up to get this format. So when we're talking about addition, subtraction, multiplication, division of complex numbers, is finding a number that looks like that. And so let's do the foiling first. So 2 times 7, which is 14, 2 times 3i, which is 6i, now plus 5i times 7, which is 35i, and then 5i times 3i, which is 15. 15i squared. Something to notice, I actually did not define the scalar multiplication of a real number times a complex number, but I used it over here. When I multiplied 2 times 3i. What I said is that it's going to multiply the real number multiplies the imaginary part, and then you put an I in front of it. Now, and over here also, when I multiply 7 by 5i, that would be 5 times 7 times I, basically. Now let's clean this up, because that's not this format yet. What I can do, add 14, and if there's any other real number. Oh, by the way, I have not used my important property over here. So let's replace I squared by -1. So this would be 14 minus 15, -1, and then add these two together to get 41i. And this is your final answer that looks like this format. So we're continuing with complex numbers. We did a few operations on complex numbers: addition, subtraction, and multiplication of complex numbers. Next thing that comes in mind is we should be able to do division. But before doing division, we want to introduce a few concepts in here. So first concept is the conjugates. So what is the conjugate of a plus bi is a minus bi. So for example, if I have 5 plus 7i, the conjugate would be 5 minus 7i. Or if I have 5 minus 7i, the conjugate would be 5 plus 7i. Now, what is the property of conjugates? So if I have a plus bi, and I multiply it by its conjugate, then what I end up with is the real part to power 2 plus the imaginary part to power 2. For example, if I have 5 minus 7i, and I multiply it by 5 plus 7i, what I end up with is and you can try this by doing your process of multiplication, and you see that two of the terms simplify together, and what you end up with is 5 to power 2 minus 7i times 7i, which is going to be minus 49. And so minus and minus positive, so it will become 25 plus 49, which is going to add up to 74. Now, division of complex numbers. And so how do we do division of complex numbers? First of all, when you're looking at the division of complex numbers, I'm going to show it as a fraction. Let's say we're trying to divide 7 plus 3i divided by 2 plus 5i. So what do I do again? Plan is for this to look like a plus bi. Right now, I don't have a plus bi. I have a complex number over a complex number. So what do? The beauty of property of conjugates is that when you multiply by conjugate, the result is going to be a real number. Look at this. A plus bi times a minus bi is equal to a squared plus b squared. And that's a real number. I disappeared. Here, the example showed you that the two complex numbers multiply to become a number 74, which is a real number. So maybe I can use the property of conjugates to actually make the denominator rather than complex become a real number. So what do? Can I just randomly multiply by conjugate? Obviously not. So what do is I'm putting another costume over this, and that's by multiplying both top and bottom by the conjugate of the bottom. So bottom becomes real. So we're trying to make the bottom real. And so I multiply top by 2 minus 5i, bottom by 2 minus 5i. And then when you're multiplying again, conjugate times the number, conjugate of that number, it's 4 plus 25. The top I have to go over and do the multiplication, so it would be 2 times 7, which is 14, plus, minus 7 times 5, which is 35i, then 3i plus times 2, which is 6i, then 3i times negative 5i, which is negative 15i squared. I squared is going to be, again, negative 1. So it would be 15 plus 14 on top. 15 plus 14 is 29. Negative 35 plus 6i, which would be negative 29. I divided by 4 plus 25, which is 29. And this actually, I can simplify this further by going 29 over 29 minus 29i divided by 29, and the answer is 1 minus I. And we're done. And that would be the same format as a plus bi, and we are done.